to two projects. In this video, we are going to explain the project Detection of Application Layer DDoS Attacks produced by various freely accessible toolkits using machine learning. Introduction. The primary objective of this project is to address the escalating threat posed by distributed denial of service, that is DDoS attacks, with a specific focus on application layer attacks. These attacks disrupt the normal functioning of websites and networks, posing a significant risk to cybersecurity. The project aims to contribute valuable insights into the detection of DDoS attacks, emphasizing the critical need to understand and mitigate the growing sophistication of these cyber threats. So, the project concentrates on the detection of application layer DDoS attacks, particularly those targeting the HTTP layer. By narrowing the focus to this specific type of cyber threat, the project aims to unravel the intricacies of attacks that exploit vulnerabilities at the application level. This targeted approach enables a deeper understanding of attack patterns, tactics, and tools used, paving the way for more effective countermeasures. And the increasing prevalence of DDoS attacks, as evidenced by a substantial rise in application layer incidents, underscores the urgent need for proactive cybersecurity measures. The project addresses the gap in current research by shifting attention from attack patterns to the tools employed in carrying out DDoS attacks. Understanding the accessibility and availability of these tools is crucial for developing robust defense mechanisms, as the ease of acquiring them contributes to the proliferation of malicious activities. And the project holds direct benefits for various stakeholders in the cybersecurity landscape. Network administrators, cybersecurity professionals, and organizations relying on online services stand to gain enhanced protection against DDoS attacks. By unraveling the methods used by attackers and exploring solutions for detection, the project aims to empower defenders with the knowledge and tools needed to safeguard digital assets. Ultimately, the broader community, including users and businesses reliant on secure online environments, will benefit from a more resilient and secure cyberspace. Objective of the project. So, as I mentioned earlier, the primary goal is to enhance the overall security of computer networks by developing and implementing advanced techniques. This involves creating robust mechanisms specifically designed to identify and counteract distributed denial of service, that is DDoS attacks, a prevalent and disruptive form of cyber threat. Strengthening cybersecurity measures is crucial to safeguarding systems against these malicious activities. And by exploring two distinct datasets, that is KDD Cup and NB-OT IoT, the project aims to deepen the understanding of network traffic characteristics. This exploration is essential for identifying patterns associated with normal network behavior as well as potential signs of cyber threats. Analyzing diverse datasets provides a comprehensive view, allowing for the development of models that are effective across a range of scenarios. And the project involves assessing various configurations of multi-layer perceptron models, a type of artificial neural network. The evaluation includes testing with different optimizers such as stochastic gradient descent, that is SGD, LBFGS, and ADAM. This objective is crucial for identifying the most effective approach to detect DDoS attacks. Each optimizer has unique characteristics, and the evaluation aims to determine which one yields the highest accuracy and reliability in identifying attack patterns. Requirements needed to execute this project are: software requirements. Software used is Anaconda, primary language used is Python, front-end framework used is Flask, back-end framework used is Jupyter Notebook, database used is SQLite 3, and front-end technologies used are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements needed are operating system of Windows, processor of i5 and above, RAM of 8GB and above, and hard disk of 25GB and above. Now we'll discuss the working models of flow of work. So the first step is importing required packages. In this step, we will import essential libraries such as NumPy and Pandas for data manipulation and analysis, sklearn for machine learning and data pre-processing, matplotlib and seaborn for data visualization. The second step is exploring the dataset. So the project involves the exploration of NSN KDD and NB-OT IoT datasets. This exploration phase includes tasks like loading the data, understanding its structure, and conducting initial data analysis to gain insights into the dataset's characteristics. The third step is data processing. So this step involves using the pandas library to create a data frame for the dataset. Data cleaning tasks are performed to handle missing values, outliers, or any other issues in the dataset. The next step is visualization using Seaborn and Matplotlib. So in this step we employ Seaborn and Matplotlib to create visual charts and graphs, facilitating a better understanding of dataset characteristics. The next step is label encoding using label encoder. Here we apply label encoding to convert categorical labels into numerical format, facilitating the training of machine learning models that require numerical input. And the next step is feature selection. So in this step, feature selection is performed to identify the most relevant features for the model. Mutual information classification is used. It is a technique used to measure the dependency between two variables, helping to select informative features. And the next step is train and test split. In this step, we segregate the dataset into training and testing subsets. The training subset is used for model learning, while the testing subset evaluates the model's performance on new data. The next step is training and building the model. So in this step, we are building 3 multi-layer perceptron models with different optimization algorithms SGD, LBFGS and ADAM. These are popular optimization algorithms for neural networks. And in the next step, that is extension phase, a hybrid model was created by combining predictions from multiple models for improved accuracy. Additionally, a user-friendly Flask-based frontend with authentication was developed. And the next step is Flask framework with SQLite for sign up and sign in. So in this step, we integrate user registration and login functionalities into the Flask framework. Users can sign up by providing their information, and subsequently they can securely log in using their credentials. This enhances system security and allows for personalized user experiences. So after signing in, users provide input through the front-end interface. The input data is pre-processed to prepare it for prediction by the trained models. This pre-processing step ensures that user-provided data is in a suitable format for the model. And the pre-processed user input is fed into the trained models for prediction. The best performing model is selected to make predictions based on the input data. And the predicted outcome is displayed through the front-end interface, allowing the user to view the results of the model's predictions or analysis. Now we'll understand about the algorithms used. So the first algorithm built is MLP combined with SGD, that is stochastic gradient descent. So first we'll understand about MLP. So an MLP, that is multi-layer perceptron, is a type of feed-forward artificial neural network comprising an input layer, one or more hidden layers and an output layer. Neurons in each layer are connected to those in the next layer, and the network uses activation functions to process information. MLPs are commonly used for tasks such as classification and regression, leveraging supervised learning with backpropagation for training. And SGD, that is stochastic gradient descent, is an iterative optimization algorithm commonly used in training neural networks. The core idea is to update the model parameters in the direction that minimizes the loss for each training example. Unlike batch gradient descent, which computes the gradient of the entire dataset in one go, SGD processes one training example or a mini batch at a time. This stochastic nature makes it computationally efficient and allows the model to adapt quickly to changing patterns in the data. And in the context of this project, SGD is a suitable choice due to its efficiency in processing data in mini batches. And the next algorithm built is MLP combined with LBFGS, that is limited memory Broyden-Fletcher Goldfarb-Shannon. So LBFGS is a quasi-Newton optimization algorithm designed for unconstrained optimization problems. LBFGS belongs to the family of quasi-Newton methods which aim to find the minimum of a function without explicitly computing its derivatives. LBFGS maintains an approximation of the inverse Hessian matrix to iteratively update the model parameters. It is particularly effective in scenarios where the dataset is not extremely large and the model has a moderate number of parameters. And the last algorithm built is MLP combined with ADAM, that is adaptive moment estimation. So it is an adaptive learning rate optimization algorithm that combines elements from both momentum and RMS prop. It adapts the learning rates of each parameter individually based on their past gradients, making it well suited for scenarios with sparse gradients or noisy data. ADAM is known for its efficiency and is often the default choice for many deep learning tasks. It includes mechanisms to control both the step size and the exponential decay of post gradients. So now we'll see the comparison graphs of the models built using NSL-KDD dataset. So this is the horizontal bar graph comparing accuracies of different algorithms. So in this graph on x-axis I have accuracy scores and on y-axis I have algorithm names. Accuracy measures the overall correctness of predictions, showing the percentage of correctly classified instances. And this is precision score comparison graph. In this graph on x-axis I have precision scores and on y-axis I have algorithm names. So precision measures the accuracy of positive predictions, indicating how many predicted positives were actually correct. This is recall score comparison graph. In this graph on x-axis I have recall scores and on y-axis I have algorithm names. So recall measures the ability to identify all relevant instances, showing how many actual positives were correctly predicted. And this is F-score comparison graph. In this graph on x-axis I have F-scores and on y-axis I have algorithm names. So F-score combines precision and recall into a single metric, balancing accuracy and completeness in predictions. So the algorithm which is best performing in all the performance metrics will be used for predictions. And now we'll see the comparison graphs of the models built using NB-OT IoT dataset. So this is the accuracy score comparison graph. This is precision comparison graph. This is recall scores comparison graph, and this is F-score comparison graph. Execution of the project. To execute this project, first we need to open the code folder which contains the project source code files. So this is data folder in which I have NSL-KDD and NB-OT IoT datasets on which we will train the models. This is static folder which consists of files related to CSS, JavaScript and Bootstrap. This is templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc. which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database and generating dynamic content to be rendered in the HTML pages. And these are model files which contain algorithm information. These files will be loaded into the project code during runtime to utilize the trained models. And these are Jupyter source files which contains combination of code, graphs and outputs all in one place. So Jupyter Notebook allows users to write and execute code in individual cells, making it a popular choice for data science. And this is signup.db file. This file is the database file used to store user information. So now copy the path of the code folder from the address bar of the file explorer. I'm copying it. Open Anaconda prompt. Use the command cd followed by space and paste the copied path and hit the enter button. So this command is used to change the current directory to the code folder's path. Now compile the app.py file using the command python space app.py. I'm typing python space app.py and hit the enter button. So this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address, localhost and port unless configured differently. Now copy the local link provided by the framework. I'm copying it and paste it into any web browser. I prefer Chrome. After pasting it, hit the enter button. So the home page of the project has been displayed in the browser. This is the front end built using Flask framework. So here we can see a sign up link, click on it. So if you are new users, we have to register first. Fill in these details and click on sign up button to register. And if we already have an account, we can directly log in by clicking on this link. So as you already have an account, I'm clicking on this link. So here we have to provide our credentials, username and password, and click on sign in button. So it has redirected us to the detection page, and here we can see a prediction link. Click on it. So we can execute this project using two datasets, NSL KDD and NB-OT IoT datasets. So first we'll execute it using NSL KDD dataset. Click on it. So here we have to fill in these parameters of NSL KDD. First we'll understand about them. So the first one is service. It indicates the type of network service, example HTTP, FTP associated with the connection. The next one is flag. It describes the status of a network connection, providing information on initiation, termination or errors. SRC bytes represents the bytes transmitted from the source in a network connection. DST bytes indicates the bytes received by the destination in a network connection. Count represents the number of occurrences of a specific event in the network. Error rate represents percentage of connections with source-specific errors. Same SRV rate is the proportion of connections with the same network service type. Different SRV rate represents the rate of connections with different network service types. DST host SRV count is the number of connections initiated to a specific destination host. DST host same SRV rate is the proportion of connections to a destination host with the same service type. DST host different SRV rate is the rate of connections to a destination host with different service types, and DST host error rate is the percentage of connections to a destination host with destination specific errors. So now we'll fill in these parameters. So service would be 20, flag is 9, SRC bytes would be 491, DST bytes is 0, count is 2, error rate is 0, same SRV rate would be 1, different SRV rate would be 0, DST host SRV count would be 25, DST host same SRV rate would be 0.17, DST host different SRV rate would be 0.03, and DST host error rate would be 0.04. Now click on predict button. So here we can see the predictions. So we can see there is no attack detected and it is normal. Click on prediction link. Click on NSL KDD link. We'll try giving another set of parameters now. So this time service would be 49. Flag would be 5. SRC bytes is 0. DST bytes would be 0. Count is 123. Error rate is 1. Same SRV rate is 0.05. Different SRV rate would be 0.07. DST host SRV count is 26. DST host same SRV rate is 0.1. DST host different SRV rate would be 0.05. And DST host error rate would be 1. Now click on predict button. So the result is there is an attack detected and attack type is DOS. Now we'll try giving another set of parameters again. Click on prediction and click on NSL KDD button. So I have entered another set of parameters. Now click on predict button. So here we can see the predictions. There is an attack detected and attack type is R12. So we'll try again. I have entered the parameters. Click on predict button. So this time attack is detected and the attack type is probe. So similarly we can give any set of parameters and can get the results. I have entered the parameters again and now click on predict button. So this time the attack is detected and the attack type is U2R. Now click on prediction link. This time we'll execute the project using NB-OT IoT dataset. So we have to fill in these parameters of NB-OT IoT dataset. First we'll understand them. MIDIR L0.1 weight. So it is the significance weighted mutual information for directional features with a bin width of 0.1. The next one is MIDIR L0.1 mean. So it is the average strength of mutual information for directional features with bin width 0.1. The next one is MIDIR L0.1 variance. So it is the variability in mutual information for directional features with bin width of 0.1. The next one is MIDIR L0.01 mean. So it is the fine-grained average strength of mutual information for directional features with bin width of 0.01. The next one is MIDIR L0.01 variance. So it is the fine-grained variability in mutual information for directional features with bin width of 0.01. The next one is HL0.1 weight. So it is the significance weighted entropy with a bin width of 0.1. The next one is HL0.1 mean. So it is the average level of entropy with a bin width of 0.1. The next one is HL0.1 variance. So it is the variability in entropy with a bin width of 0.1. The next one is HL0.01 mean. So it is the fine-grained average level of entropy with a bin width of 0.01. The next one is HL0.01 variance. It is the fine-grained variability in entropy with a bin width of 0.01. The next one is HHGIT L0.1 mean. It is the average mobility of a signal variations, that is jitter, with a bin width of 0.1. And the last one is HHG L0.01 mean. It is the fine-grained average mobility signal variations, that is jitter, with a bin width of 0.01. So now we'll fill in these parameters. So the MIDIR L0.1 weight would be 4. MIDIR L0.1 mean would be 83.8. MIDIR L0.1 variance would be 141.8. MIDIR L0.01 mean would be 117.3. MIDIR L0.01 variance would be 26437.9. HL0.1 weight would be 4. HL0.1 mean would be 83.38. HL0.1 variance would be 141.8. HL0.01 mean would be 117.3. HL0.01 variance would be 26437. HHGIT L0.1 mean would be 44. And HHGIT L0.01 mean would be 39.4. Now click on predict button. So here we can see the predictions, that is there is no attack detected and it is benign. Click on prediction link, click on NBOT IoT link. We'll try giving another set of parameters now. So I have entered the parameters. Now click on predict button. So here we can see the predictions, that is there is an attack detected and the attack type is gadget combo. Click on prediction and click on NBOT IoT link. So we'll again give the parameters. So I have entered another set of parameters. Now click on predict button. So we can see the result here, that is there is an attack detected and attack type is gadget junk. So similarly, by giving different sets of parameters, we can predict attacks falling into 11 different class labels. So now click on sign out link. So the conclusion here is the project significantly contributes to cybersecurity by developing advanced techniques for detecting and mitigating distributed denial of service attacks, bolstering the resilience of computer networks. And through thorough exploration of diverse datasets, valuable insights into network traffic characteristics and potential attack patterns were gained, providing a foundation for effective model development. The evaluation of multi-layer perceptron models with different optimizers including SGD, LBFGS and ADAM identified the most effective approach for DDoS attack detection, contributing to the robustness of cybersecurity measures. And the extension of the project with a hybrid model combining predictions from multiple models showcases innovation. This approach enhances prediction accuracy and resilience against diverse cyber threats. And the integration of a Flask framework with SQLite for user sign-up and sign-in, coupled with a user-friendly frontend, ensures practical applicability. Users can conveniently provide input, witness predictions, and interact with the system, enhancing real-world usability.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.